Welcome back. In the previous lectures, we have discussed several examples where the convergence is pointwise and the pointwise convergence is not preserved under integration, differentiation for different cases. So we ended the discussion by saying that under some situations, under some scenario, that will be preserved. What is that? So we now introduce the definition of a uniform convergence, and that is the notion of uniform convergence. Here we start with the sequence of functions. So here also our fn of x is a mapping from CRR. So this kind of sequences only we are considering. We say a sequence of functions converges uniformly on E. There we just have seen convergence. Here we are going to say about uniform convergence on E to a function f if for every epsilon positive there is an integer n such that fn of x minus f of x is less than or equals epsilon for all x in E. Okay, so we now closely explore about uniform convergence of a sequence, and the convergence for series follows immediately. Okay, here what is the main difference between pointwise convergence and uniform convergence? Okay, when we talk about pointwise convergence, we fix a point. Once we fix a point, your fn of x shall just be treated as some an, and we know how to check the convergence of an, and that is how we do it. Okay, in this way we find for every x, and that is how we constitute a limit function and we talk about it. Okay, the convergence of a sequence also involves this epsilon and n, and we will have this similar scenario over there. Okay, there in pointwise convergence your epsilon would be a function of x. Okay, oh sorry, we will fix epsilon, and based on which we select n. This would be a function of epsilon and the x that we are at which we have evaluated the sequence. Okay, in the case of uniform convergence, whatever may be the epsilon that we choose, we will have to identify some n that is completely based on epsilon, not on x. So the same n has to work for all x in E. Okay, so if we are able to identify one uniform n for whatsoever the given epsilon, and if one such function exists, yes, we can say that this converges uniformly. So basically this uniform convergence is kind of a global property, just like our uniform continuity, and pointwise convergence is a local property, just like continuity at a point. Okay, so from this we would be able to observe that convergence uniformly will imply pointwise convergence. Okay, now to check the uniform convergence of a series, construct a partial sums, sequence of partial sums, and examine its convergence. Next, we are going to discuss about Cauchy criterion for uniform convergence, which says we have a sequence of functions which converges uniformly on E if and only if for every epsilon positive there exists an integer n such that m bigger than or equals n bigger than or equals n implies this. So if we prove it is uniformly Cauchy, that is enough to say that it converges uniformly, right? So we will just see the proof. Now let us suppose fn of x converges uniformly. Then for every epsilon positive there exists n in n such that absolute of fn of x minus f of x is less than epsilon. I am just taking it as epsilon upon 2 for n greater than or equals n. Okay, I just applied the definition of uniform convergence. So similarly, we would be able to get fm of x minus f of x is less than epsilon upon 2 for m bigger than or equals n. Now let us consider absolute of fm of x minus fn of x. This is, we just add and subtract f of x to it. Now using triangle inequality, this is fm of x minus f of x plus fn of x minus f of x. Yeah, it is fn, right? Yeah. So each of this quantity is smaller than epsilon upon 2. So this is what we have. So we just established fm of x minus fn of x is less than epsilon for all n bigger than or equals n and m bigger than or equals n. So we have established the one way. Now let us suppose the converse. Conversely, suppose the Cauchy condition holds. That is, suppose absolute of fm of x minus fn of x is less than epsilon for all n bigger than or equals n, m bigger than or equals n and x in E. Okay. Since it is a Cauchy sequence. Okay. Now let us just fix x in E. Okay. We are supposing. Okay. So for every x in E, like we are fixing, that means we are taking a particular x, but it can be done for any x. Okay. So instead of fixing for x in E, we have this thing. Okay. For x in E, we have fn of x is Cauchy in either C or R. Both of these are what? Both of these are Euclidean space, complete metric space, which means that our fn of x converges to some f of x. So this can be done for every x. That is why we establish some pointwise convergence. Okay, that is fn of x converges to f of x pointwise. Now the convergence is established. Now we will have to justify that the convergence is uniform. For that purpose, let us take epsilon to be positive. Let it be given. Let us choose n such that absolute of fm of x minus fn of x less than epsilon. Okay. Let m go to infinity. Then what will happen? Fm of x will go to f of x. So this will imply that absolute of f of x minus fn of x is less than epsilon for all n bigger than or equals n and x in E. So which just proved fn of x converges uniformly to f of x. We just completed this theorem. Okay. Since we are dealing with real sequences or complex sequences, it is enough to justify that the given sequence is Cauchy in order to prove it converges uniformly. Okay. And so further, we have the following two theorems. The first theorem says that if the pointwise limit is f of x, okay, and if we have this mn, which is the supremum of absolute of fn of x minus f of x, where f of x is the pointwise limit of Fn of x. Okay, then the convergence to this pointwise limit will be uniform. This convergence will be uniform if and only if this Mn converges to 0 as n approaches to infinity. This is just an immediate consequence of the definition. And if we like, this theorem is known as Weierstrass test for uniform convergence, Weierstrass M test. Okay, the next theorem that we have is for the series of functions. We basically have a sequence of functions defined on a set E, and that function is pointwise bounded. Okay, for each n we are able to identify corresponding thing. Okay, so this boundedness is there, then this summation Fn converges uniformly if summation Mn converges. Okay, we just consider here, we are not going to prove this completely, maybe a hint will work. Okay, suppose summation Mn converges, then what? Then since it is a series in real numbers, positive real numbers, it has to satisfy the Cauchy criterion, right? Then for given epsilon positive, what do we have? We will have summation I runs from n to m, mi would be less than or equals epsilon. Okay, here what is summation I running from n to m? Fn of x, absolute of this quantity, is less than or equal summation I running from n to m, absolute of Fn of x, and each of this value is smaller than or equals mi, which is given to be less than epsilon. So this means that your absolute of summation I running from n to m Fn of x is less than epsilon, right? So this is for n comma m bigger than or equals n. For this condition only this holds true. This shall be written as Sm minus Sn is less than epsilon. I think n minus 1, isn't it? Yeah, less than epsilon for n comma m bigger than or equals n, where your Sn is nothing but summation I running from 1 to n Fn of x, Fi of x. Okay, here also it is Fi of x. Now that what we have just established is that this sequence of partial sums converges by the theorem that we have just discussed. Okay, so this just proved summation Fn of x converges uniformly. Okay, to what limit, that we don't know. As of now we don't know the limit of the convergence, but we have just established that it converges uniformly. That's it. In the upcoming lecture we will work out few problems based on the theorems that we have discussed. Thank you.